Hello friends, today we will discuss an experiment of Quincke's method. This is the setup for the Quincke's method. The aim of the experiment is to determine the mass susceptibility of paramagnetic solution by Quincke's method. The apparatus we will be using are Quincke's tube fitted on the stand, which is a U tube. One limb of it is narrow and the other is broad. Electromagnet capable of producing magnetic field of about 10 kilogauss with its power supply, a Gauss meter and Hall probe, a traveling microscope to measure the rise in liquid, and the experimental solution, which in our case is ferric chloride solution of 50% and 100% concentration. Faraday divided the magnetic materials into three classes. The diamagnetic substances. These are the substances which, when placed in a magnetic field, are feebly magnetized in a direction opposite to that of the magnetizing field. For example, copper, gold, antimony, silver, lead, hydrogen, etc. Then paramagnetic substances. These are those substances which, when placed in magnetic field, are feebly magnetized in the direction of the magnetizing field. Platinum, aluminium, manganese and solutions of iron and nickel are some of its examples. And finally, the ferromagnetic substances. These are the substances which, when placed in a magnetic field, are strongly magnetized in the direction of the magnetic field. Iron, nickel, cobalt and their alloys are some of the examples. Now let us see what the magnetic susceptibility is. So as we know that when a magnetic material is kept in a magnetic field, it gets magnetized. So magnetic susceptibility is a measure of the ease with which a specimen of that material can be magnetized by a given magnetic intensity. So it is defined as the ratio of the magnetization M produced due to the magnetic intensity H. So as it is a ratio of the two magnetic fields, therefore it is a dimensionless proportionality constant. Diamagnetic substances have negative susceptibilities and paramagnetic substances have small positive susceptibility, and the magnetic susceptibility of ferromagnetic substances is positive and very high, of the order of 10,000. When a solution of a paramagnetic substance is taken in a tube and placed between the poles of a magnet, there is a rise in the liquid level because the paramagnetic substance tend to move in the direction of the magnetic field. So a measurement of this rise in the level of the solution enables us to determine the susceptibility of the substances. So in our present experiment, an experimental solution, which is ferric chloride in our case, is placed in the Quincke's tube as shown here. And the narrow limb is kept within the magnetic field. So this magnetic field provided by the electromagnet, it varies rapidly along the vertical direction due to the wedging of the poles. So as it is acting in the vertical direction, so there will be a rise in the liquid level
when the current is switched on. So the formula used for finding out the mass susceptibility for the liquid is given by chi m is equal to 2 mu naught g h upon b square, where mu naught and g are the constants. H is the rise in the liquid level in meters and B is the magnetic field applied in Weber per meter square. Now let's perform the experiment.
So here we have the actual experimental setup used for Quincke's method. This is the electromagnet which is supplied with the constant current supply. We can change the current up to 3.5 amperes. Now this is the Gauss meter which is connected to the Hall probe. This is our Hall probe, and which when kept in the magnetic field senses the magnetic field and is read in the Gauss meter. Now these are the experimental liquids of 100% and 50% concentration. They are kept between the magnetic field, and this is the lamp to illuminate the view.
This is the traveling microscope, which is able to move in horizontal as well as in vertical direction. So this is the microscope of it, and a crosswire is set on the liquid meniscus. Then this is the main scale, and the smaller one is the vernier scale. So we take the readings with the help of this, as we take in case of the vernier calipers.
This is the fine screw adjustment. If we have to move it by larger distance, we use the other screw to move it. But when we have to move by the small distances, we use this fine screw.
During the experiment, mostly we will be using fine adjustment screw.
Now let's start the experiment. So first of all, we have placed the Hall probe between the magnetic field to measure the magnetic field as per the current. So this is the constant current source is giving 0 current at this moment, and so we will adjust the Gauss meter with the help of 0 adjustment to 0 value if possible. So here in our case there is some error, so we will take this 0 error. So this is 50 Gauss because the multiplier is on 10. So here for 0 current we have 50 Gauss. Then we will change the current to say 0.5 amperes and see how much is the magnetic field. So we will note it down in our table. Again change the current to 1 amperes and note down the magnetic field. Here we are getting the magnetic field in Gauss. So this process we will continue till we get the magnetic field corresponding to the current of 3 amperes at a difference of 0.5 amperes. Now we will remove the Hall probe and put the narrower limb of 100% concentration solution between the magnets. Now focus the microscope on it, on the meniscus properly. One thing to be noted that here the meniscus will be seen inverted because the microscope gives us the inverted image of it, and similarly the rise in the level will be will be seen as fall in the level. So that will this is the meniscus of it, and this is how we will put the crosswire of the microscope. Now on the right hand side you can see upper the meniscus of the liquid level going down because it is giving the inverted image with increase in current. Similarly, when we decrease the current, it appears to rise. Actually it is the level is falling down. Now let us focus the microscope on the liquid meniscus and try to take the reading. So the reading of the main scale would be the division which is on with the 0 of the vernier or before the 0 of the vernier. So if with the help of this lens we can see that 3.2 centimeter is the main scale reading, and the 10th division of the vernier scale is in coincidence with the main scale. So 0.1, because 10 multiplied by the least count would be the reading of the vernier scale. So we'll note down that that will be our initial reading. Now we will increase the current to 0.5 amperes, and then again that time the focus of the microscope would be disturbed. We will focus it again, bring the crosswire back to the with the level of the meniscus with the help of the fine adjustment screw. and then take the readings. Again, change the current and take the readings of the traveling microscope. This process we continue till 3 amperes with a difference of 0.5 ampere of current. So after that, we remove this 100% solution and place the 50% solution between the magnet, and then follow the same procedure. That is, first we will adjust it for the zero current. That would be our initial reading for 50% solution, and then increase the current 0.5 amperes, adjust the crosswire with the help of fine adjustment screw, and then take the reading of vernier and main scale of the traveling microscope. So this process again we will follow till we get it for till the 3 amperes reading with a difference of 0.5 amperes. We will note down all the readings in our observation table and see how to perform the calculations. This is our observation table for the ferrochloride solution. So we have taken the current, and then corresponding magnetic field is noted down, the first part of the experiment. Then we will take the 100% solution between the magnetic poles and adjust the crosswire at the liquid meniscus and take the reading of the vernier scale and main scale. So that will give us the initial position for that that concentration of the solution. So we'll note down that initial reading will be same for all the currents, for all the cases. After that, we increase the current to 0.5 amperes say, and then again adjust the crosswire or at the liquid meniscus and note down the position of the traveling microscope. So say that is H2 and the initial reading was H1. So H2 minus H1 will give us the rise in liquid level for 0.5 amperes of current. Similarly, we will take the readings for 1 ampere, 1.5 ampere, and each time we will subtract the reading, final reading with the initial reading to get the rise in liquid level for that particular current. So this is the type of graph we will get when we plot it for the magnetic field square versus rise in liquid. This is the graph I have plotted for my actual reading which I have taken here. So we will take the slope of the line, that is H versus B square curve. Slope would be noted down. So we will be plotting graph for each concentration B1 B square in along the x-axis and H along the y-axis. So the slope would be calculated in centimeter per kilo Gauss square. So we have to convert this into meter per Tesla square and then substitute the value in the formula chi is equal to 2 mu naught g into slope. So we will calculate this for both the concentrations, and we will report our results in the form of following table. So the final results are reported in the following table. So for 50% solution, mass susceptibility, and then for 100% solution. Now the precautions. We have to adjust the microscope to get a clearer picture of the meniscus and adjust the crosswire exactly on the meniscus. After focusing the microscope and adjusting the crosswire, while taking the readings of the vernier and main scale, use lamp and magnifying glass. It will give you the clearer image, clearer view, and it will be easy to take the readings. And let the liquid rise and become steady before taking readings of the meniscus. And then you should be very careful while drawing the best fit line while plotting the graph for H versus B square, and then carefully take the slope. That's all about this experiment. Thanks for watching. Have a nice day.